Hey, it's Moser, and we're going to derive two more equations together. So far, your note card should look something like this, with your basic average velocity and average acceleration equations, plus the first of our four golden equations, delta x equals 1/2 delta t times the quantity vi plus vf. Well, what if we need to find displacement, but we don't know the final velocity, and we don't have an easy way to compute it? We're going to take a couple steps to get there, but we can do this. The two things that we'll have to know are delta t and our rate of acceleration. And the rate of acceleration will have to be constant. If that's the case, we can start off with this. Now, I know what you're saying. My delta v is going to require my vf. Yep, be patient. This is not where we're going to end up. But we are going to pass through an equation that uses vf. So let's rearrange that. We know that delta v is equal to vf minus vi. So we're going to rearrange to get acceleration is equal to vf minus vi over delta t. Okay, no rocket science here yet. We're going to solve this for vf. We get a delta t plus v equals vf, or as I prefer to put it, vf is equal to vi plus a delta t, which if you think about it is really just a pretty clear expression of truth. Your final velocity is equal to how fast you were going when you started, vi, plus your rate of acceleration times the amount of time that you've had to accelerate. Hey, while we're at it, we should probably put that on the note card. That'll be the second of our golden equations. But wait. We wanted to find displacement when we didn't know vf. Okay, let's get to that. Okay, so we've just pulled over our vf equals vi plus a delta t. Now, you remember our first golden equation? Delta x equals 1/2 delta t times the quantity vi plus vf. Ooh. I see a substitution coming. Yes, that's right. We're going to take the equation that we've created for vf, and we're going to jam it sideways into this other equation. Woohoo! Okay, now, it looks a little ugly right now, but we're going to improve upon that. I promise you. So, this underlined portion in red is the part that we substituted in. To start off, let's distribute the 1/2 delta t across the other portions of the equation. That's going to look like this. Oops, I misspoke. Let's not do that first. First, let's combine all the terms that we can inside the parentheses. That's a much better idea. Well, immediately, we know that we'll be able to combine these, and we'll get 2vi. This is already looking less ugly. Now let's go ahead and distribute the 1/2 delta t. Okay, we have delta x equals 1/2 delta t 2vi plus 1/2 a delta t times delta t. Let's do a few things. When we multiply 1/2 by 2, guess what? It goes away. When we multiply delta t by delta t, we get delta t squared. Let's rewrite that. Hey, that's not so ugly. What we have is delta x equals vi delta t plus 1/2 a delta t squared, which means that as long as we know our vi, delta t, and a, we can find displacement, even if we have no clue what the final velocity is. Let's add that to our note card, shall we? Okay, so we now have the first three of our four golden equations. Let's look at the 2D sample problem, and then you'll do the 2D practice problems on your own. We're told that a plane starting at rest at one end of a runway undergoes a uniform acceleration of 4.8 meters per second squared for 15 seconds before takeoff. What's its speed at takeoff? And how long does the runway have to be for the plane to be able to take off? So we're really asking two things here. Let's list the variables we have for the first one. The first four variables that we're starting with are vi, vf, a, and delta t. What's vi? Well, the plane is at rest. vi is equal to 0 meters per second. Final velocity is actually what we're being asked about in the first part of the problem, and we're given an average acceleration of 4.8 meters per second squared for an interval of 15 seconds. So what equation do we have that ties these four things together? Because that's how we look at these problems every single time now. Well, we've got our old friend VF equals VI plus A delta t. That would work. Especially easy because there is no VI. VI is 0. And in any situation where VI is 0, we can just get rid of it. So let's plug in our numbers. We don't even have to rearrange and see what our answer is. We see that VF equals 4.8 meters per second squared times 15 seconds. Let's not forget to do our dimensional analysis, shall we? Meters per second squared times seconds would give us meters seconds over seconds squared, which would give us meters per second. That's convenient since we're looking for velocity. Okay, raw answer is 72 meters per second, even, and that's already got 2 sig figs, which is the maximum we can have. So our answer for this part of the question would just be 72 meters per second. That's the velocity of the plane at takeoff. Now, if we hadn't found final velocity, if we hadn't done this somehow, could we still figure out the displacement that would be needed for this plane to take off? Of course we could. I'm going to shrink my part 1 stuff and set it aside, and I'm going to list my variables for part 2. So in part 2, we're looking for delta x. We are working with the same acceleration, the same time interval, and we have the same initial velocity, namely 0 meters per second. Well, this one calls for, ta-da, delta x equals VI delta t plus 1/2 A delta t squared. Lovely. For no good reason whatsoever, this is actually my favorite of the kinematics equations. There is no rational reason for that. So let's look at one thing first. Since the initial velocity is 0, this entire portion of the equation is going to disappear, leaving us with delta x equals 1/2 A delta t squared. Pretty cool. We plug in our numbers to see that delta x is equal to 1/2 times 4.8 times 15 seconds. We get a raw value. We get a raw value if you don't forget to square your time. There's a great thing for the mistake game. Delta x equals 540 meters. Basically, you need a 1/2 kilometer long runway to get this plane off the ground. How many sig figs can we have? 2, and that's what we've got. So our answer for the second half of the problem is 540 meters. The 2D practice problems in the book are assigned, all of them, and when you're done with that, there should be a 2D worksheet over on the lab table. Keep working.